Alright, in this video we're working BC Homework 9.4, and so we're going to do some of the integrals where we have to complete the square that are involving arc trig, and then we're going to work some other integrals that kind of look similar to those ones that involve arc trig but are somehow slightly different. Okay, so the first one we've got is 15 over x squared minus 15x plus 50. And 50 is one bigger than a perfect square, so that's something we have to look out for, but I don't think that that's going to be one bigger than a perfect square because of that negative 15. So I'm thinking about this, and I'm looking at the denominator, and I'm like, oh wait, this is factorable. I can work with that. And if the denominator is factorable, we're going to split up the denominator using partial fractions. So I'm going to say, okay, 15 over this denominator is going to be a over x plus 5 plus b over x plus 10. Multiply both sides by both denominators. Get 15 is a times something plus b times something else. Let's start by letting x equal negative 5. That'll give me 15 equals 5a, which means that a equals 3. Then I'll need x equals negative 10, which will show me that b is negative 3. Okay, so I kind of rewrite my integral. Now I can factor out the 3 if I want, but you don't have to if you don't want. And then I'd have 3 natural log of x plus 5, negative 3 natural log of absolute value of x plus 10 plus c. You could, factor out the 3 if you wanted to, or distribute it through like that, and it really doesn't matter. Now number 2, 15 over x squared minus 14x plus 50. I'm thinking about factors of 50 that add to negative 14, and that's not going to work. Because we had 10 and 5, and that was 15, and 25 and 2, 50 and 1, and 5 and 10. Oh, we already talked about 5 and 10, but this isn't not going to be factorable, right? And so if it's not factorable in the denominator, it must be complete the square. And I think about it, okay, x squared minus 14x plus 49 would be a perfect square. So this one's going to be the one that involves arctangent. Okay, so I'm going to say, all right, I'm realizing this is one bigger than a perfect square. 1 over x minus 7 squared plus 1. That's a pattern that we need to be able to, or start growing to recognize. I've got a little bit of practice here, and if you're not recognizing the patterns, let me know, and I can write down a bunch of other ones for you. Okay, so here it's going to be, an antiderivative for this is going to be 15 arctangent of x minus 7. And we're going to let x go from 7 to 8, so we'll start by plugging in x equals 8 and get 15 arctangent of 1, plug in x equals 7, get 15 arctangent of 0. And this is where we have to remind ourselves, okay, arc whose tangent is 1, the most obvious place on the unit circle where tangent theta equals 1 would be at theta equals pi over 4. So I'm going to have 15 pi over 4 minus 15 arctangent of 0. Arctangent of 0, the most obvious place on the unit circle where tangent theta equals 0. That'd be theta equals 0. So I got 15 pi over 4 minus 15 zeros, and that's going to be 15 pi over 4. I've got 15 over x squared minus 10x plus 25, and that is a perfect square. That's going to be x minus 5, x minus 5. So I'm going to say, all right, whoops. Okay, I think that's what I wanted. 15 over x minus 5, x minus 5. Okay, well, that's x minus 5 squared in the denominator, and since I'm integrating, I might be wise to write that as 15 times x minus 5 to the negative 2 in the numerator. So I can anti-differentiate. Okay, I'm going to apply the power rule, and so I'm going to add 1 to the power and divide by the new power, so that's negative 15 of x minus 5 to the negative 1 from 7 to 8. Okay, plug in the bounds. Maybe I'll rewrite first, kind of got in that habit in the last lesson when we were doing all those improper integrals, but okay, so negative 15 over 8 minus 5 minus negative 15 over 7 minus 5 is negative 15 thirds plus 15 halves. It's like, okay, negative 5 plus 7.5 is going to be positive 2.5. I'm seeing as I'm doing that I kind of missed a negative right there. Whoops. See that? How about there? Yeah. Okay, there we go. All right, so that's looking right. Okay, so this next set of threes, I don't know, got a little bit more intrigue to it. So I've got 1 over 2x squared plus 4x plus 4, and I am noticing the 2, 4, and the 4, they're all even numbers, so I know in some sense this is definitely going to be factorable. So I'm going to factor the 2 out of the denominator, and I'll be left with x squared plus 2x plus 2. It's like, that's not factorable either. It would need to be x squared plus 3x plus 2, or x squared plus 2x plus something else. Yeah, 2x plus 1 or something. Yeah, and, like, it's not factorable, so it must be one larger than a perfect square. And if you think about it, x plus 1 times x plus 1 would be x squared plus 2x plus 1. So I am 1 larger than a perfect square in the denominator. So I'm going to factor out the half and then realize, okay, now the denominator is 1 bigger than a perfect square, so I'm going to have 1/2 arctangent of x plus 1 plus c. And then number 5, because it's just 36 minus x and inside the square root in the denominator, it doesn't look like I should be able to, but I will be able to just apply the power rule to this. So I think we'd be wise to write this as the integrand as 12 times 36 minus x to the negative half power. And then I'm going to add 1 to the power, divide by the new power, so it'd give me 24, and then kind of like double check for the chain rule. Okay, because the derivative of 36 minus x is negative 1. Okay, I'm going to divide by that negative 1 to prepare for the chain rule. And then if you wanted to, you could rewrite as negative 24 square root of 36 minus x plus c. Okay, but that would be the same as the expression I'd written right above it. Okay, then for number 6, once I put that x squared in the denominator, I'm not just going to be able to add 1 to the power, divide by the new power, and divide by the derivative of the inside. That would end up divided by 2x or negative 2x or something. And that would cause an issue if you tried to, check by taking the derivative because of the quotient rule. So what we're going to do instead is realize this, okay, square number minus x squared inside a square root in the denominator, that's got to be related to arc sine. So I think what I'm going to do is factor out the 12, so at first I don't get distracted, right? Yeah, factor out the 12 from the numerator, and then also factor out the 36 from inside, kind of like inside the square root in the denominator. So 36 times 1 minus x squared over 36. Then we're going to apply that radical property like I showed you in class. You're going to be thinking, okay, factor out the 1 over the square root of 36. Probably should have shown that step, but I think I'm going to do another one of these later where I'm a little more explicit with steps. But that square root of 36 times the square root of 1 minus x squared over 36, okay, that square root of 36 is the 6 that's coming outside the integral and becoming the 12 over 6. So at this point, it's like, okay, 1 over the square root of 1 minus the thing squared, the antiderivative of that should be related to arc sine. And so the 2 is the 12 over 6. The multiplication by 6 is because of x over 6. I'm kind of like preparing for the chain rule right there. And then I'm adding c, so I could call that 12 arc sine of x over 6 plus c. And if you wanted to, you could check that by taking the derivative and showing that, after taking the derivative of everything, you can get it all worked around to be just right and equivalent to 12 over the square root of 36 minus x squared. Number 7 is kind of still related to the other ones, this 12x over the square root of 36 minus x squared. Now, I think I had meant for this to be the integral from 0 to 6, but it says the integral from 0 to 5, so I'm going to kind of stick with it. So with this one, since I've got the 36 minus x squared inside the square root in the denominator and the 12x in the numerator, that x is really in the way. It's not going to be related to arc sine. I'm going to have to use a u substitution because the derivative of 36 minus x squared, well, it's going to be proportional to 12x. So I'll let u equal 36 minus x squared, meaning du is negative 2x dx, but I don't really have that. I have positive 12x dx. So I'm going to multiply both sides by negative 6. I'll have negative 6 du equals 12x dx. And now I'm going to convert the bounds. When x is 0, u equals 36 minus 0 squared. So u will equal 36. And when x equals 5, u is going to equal 36 minus 25, which is going to be 11. That's going to leave me with kind of a weird number in there. But that's all right. It's not the end of the world. So I'm going to convert my integral. I'm now going to be integrating from 11 to 36 on, okay, that 1 over the square root of u is still there, but the 12x dx became a negative 6 du. And now that I've got my bounds converted, I can stick totally to u for the rest of the problem. It's not an improper integral or anything, so I don't have to be all that careful. I'm going to anti-differentiate, plug in the bounds, and subtract, and then it's like, okay, negative 12 root 11 plus 12 root 36, that's going to be 72 minus 12 root 11. Okay, for number 8, okay, x squared plus 36 in the denominator, it's like, oh man, this is going to be related to arctangent, because if it was just x squared plus 1, it would be 12 arctangent of x, and we'll be able to do some algebra on this one, manipulated. I think it's going to have to do with x divided by 6, again, just like the other ones. So I'm going to say, all right, factor out the 12 first. And then also maybe factor out the 36. Okay, hopefully I showed you this in class, showed you this algebraic manipulation, and told you it's going to work the exact same way every time with the ones that fit into this pattern. So I'm going to factor out the 1 over 36, okay, out of the whole integral, so I have 12 over 36, and then I have the integral of 1 over 1 plus something squared. And that's where I'm going to be thinking about arctangent. So I've got the 12 over 36, arctangent of x over 6, but because of that x over 6, the derivative of 1/6 of x is going to be 1/6. So I divide by 1/6, which is like multiplying by 6. That's where that extra factor of 6 is coming in. And then I have, okay, 12 times 6 divided by 36. You could look at that as 12 over 6, or however you're going to simplify that. That's 2 arctangent of x over 6 plus c. And then number 9, I think we actually did this exact one in the notes, but it looks pretty similar to some of the other ones we've done, the integral of the square root of 36 minus x squared. And we need to know that when we're looking at that integral from 0 to 6, we can do that one with geometry. So we need to know that y equals the positive square root of 36 minus x squared makes the upper half of a circle centered at the origin, has radius 6. And then I'm going to say, okay, if I'm integrating from 0 to 6, that'll be that portion of the circle. So it's a quarter of a circle, 1/4 of pi radius squared. That's going to be 36 pi divided by 4. That's 9 pi. All right, next, we've got some improper integrals. And so when we say, or show that it diverges, that's a good hint, but we've also got that infinity in the bounds of integration, so that's another kind of hint of what we got going on here. So looking at this and saying, okay, well, x squared plus 2x plus 1, I can factor that. That's x plus 1, x plus 1. And if it's a perfect square, I might just go ahead and write that as x plus 1 to the negative 2 power. And so I've got x plus 1 to the negative 2 power. That's an improper integral, so I have to write two limits. Okay, the first limit needs to be the limit of an integral, so that's going to be the limit as b approaches infinity of the integral from 1 to b of the same integrand. And then there's going to be a limit of something else I need to evaluate to determine whether or not the integral converges. But figuring out what goes on the inside of those kind of square brackets, I'm going to go off to the side and do some scratch work. I'm going to say, okay, the integral from 1 to b of x plus 1 to the negative 2, I'm going to anti-differentiate, rewrite, okay, and say, okay, negative 1 over b plus 1 minus negative 1 over 1 plus 1. Okay, that's negative 1 over b plus 1 plus a half. So I'm going to put that into the limit and think about as b approaches infinity, that negative 1 over b plus 1, that's going to go towards 0. And I'll have 0 plus a half equaling 1/2. Okay, so that one converged. And then if I'm looking at number 11, okay, this one's pretty similar, like the integral from 0 to infinity of 1 over second power in x. This one should probably also converge, but, it might be looking a little bit different, right, because of it being 1 bigger than a perfect square in the denominator. So that's what you're supposed to notice. Okay, I just did x squared plus 2x plus 1 in the denominator. X squared plus 2x plus 2 in the denominator is 1 bigger than a perfect square. So this is going to activate that arctangent pattern. So I recognize that it's an improper integral. I'm going to write the limit of the integral and kind of set up to take the limit of something else, but that something else that I need to take the limit of, I'm going to do that off to the side. So the integral from 0 to b of 1 over the square of x plus 1 plus another 1, that's going to be arctangent of x plus 1. Okay, we're going to let x go from 0 up to b. And so I'll have arctangent of b plus 1 minus arctangent of 1. Remember, arctangent of 1 is going to be pi over 4. And, okay, so I guess I can write that down now. That might be a good idea. I'll save myself some room off to the left. And then I'll say, okay, well, the limit as b approaches infinity of arctangent of b plus 1. Well, you think about, okay, as b approaches infinity, so does b plus 1. And the limit of arctangent as the argument goes towards infinity is the arc on the unit circle. The most obvious place on the unit circle where tangent approaches infinity, that's pi over 2. So I'll have pi over 2 minus pi over 4, and that's going to be pi over 4. All right, now that's probably all of the new stuff I've got to show you for this homework. I do have some extra practice on U and TV, and then I guess some extra practice on the next page on more complete the square, and maybe I'll give you some more detail on that one. But for these UDV problems, I'm just going to kind of show you the answers real quick, because that's really not the focus of this video. I just thought it had been a few days, and it might be good for us to continue practicing our U and TV, especially like number 13. We had one like that on a quiz somewhat recently where people were not executing the second integral properly. So I think it's just good that we're sticking with UDV. We're doing really good on partial fractions, at least this year, and I assume whenever you're watching this video, we're going to be having success on the A and the B in my class. So let's just do a little bit more practice on UDV. So number 12, isolate algebra before trigonometry. You're going to see I'm going to use the chart quite a bit on this one because I was interested in getting these antiderivatives done quickly, and also the first one was u equals 8x squared. So I kind of felt like maybe I'd have been wise to, use the chart method because u was some number of x squareds. Okay, for number 13, 8x squared log x, I laid log before algebra, so u equals log x. And really it was that second integral, that integral of 8/3 x squared dx. When I was grading a quiz recently, I found people were not simplifying that I'd have 8/3 x to the third times x to the -1 dx, and people were not simplifying before they anti-differentiated, getting themselves something totally wrong. So it's like, okay, remember that that's a really important step in solving one like that, where u equals log x and dv is something algebraic in x. That's, we're good at those, just provided that we make that simplification. All right, number 14, 8x e to the x over 2. Okay, I'd kind of set up a chart, and because u is just some number of x's, u is algebraic and whole number power, I could use the chart technique. Number 15, u equals x squared. I'm definitely going to want to use the chart for that one. Just kind of, it's like, well, it's working for me. Kept doing it. I think soon enough I'm going to get one where, yeah, this one didn't work out so well because I don't know how to do the chart method when u is arctangent x. Okay, so this one worked out all right. I go and I do all the stuff, and the second integral is like x squared over x squared plus 1, and the equal degree on top and bottom, so I needed to do some long division, and the long division was actually pretty nice. So there you go, and I was able to do that integral. But then number 17, I feel a little bad about that one. I guess I just thought, x arctangent x was going to work. I first saw that coming, and then I thought about x arc sine x, and I was like, oh, might as well do one of those two, because I hadn't used the I and isolate very much. But it kind of led y'all into a trap where I do believe that second integral is something that you can take with a slightly more clever u substitution. But I'm going to just leave it there and point out, I thought my first idea for a u substitution did not work out on that. So I'm sure I could just look it up on the internet, but I think it would be best for me to remind you this one is beyond the scope of AP Calculus. Probably number 16 also. Number 16 would be really intense. I think that one's technically inbounds, but man, number 17, I know that second integral is not something you'd be expected to do in this class, so I'm just going to leave that one there. Alright, now with this last set of problems, these are pretty similar to the other ones. Complete the square, so these are the ones we're going to have to do some algebra on them. And yeah, because, oh no, I did do one that was one bigger than a perfect square, but those are pretty recognizable. It's the other ones that we need to make sure we're practicing. So this 1 over 100 plus x squared, this is exactly one of the ones I'm talking about. So we're going to start out by factoring the 100 out of the denominator. And then I'd have 100 times 1 plus x squared over 100. But I know that I'm going to eventually write that as x over 10 squared. So if you see that coming, you might as well just go for it on the first step. Okay, and then maybe get rid of that 1 over 100 and think about this for a second. Okay, arctangent of x over 10. But I would need to divide by that 1/10 to prepare for the chain rule. So I multiply by the 10, I get 10 over 100. If this was multiple choice, you could easily recognize 10 over 100 is the same as 1 over 10, but that's going to be my antiderivative. For number 19, 2x squared and 50, I can factor the 2 out of both of those. So I think that's where I'm going to start, is factor out the 2 from the denominator, pull that outside the integral, so I have half of the integral of 1 over x squared plus 25. And this one, it's going to look very similar to number 18. I'm going to factor the 25 out of the denominator. And so I'd have a half that I already had, the 1/25 that I'm factoring to have 1 plus something squared, and that thing would be x squared over 25, which is the square of x over 5. And so then I'm thinking, okay, 1 over 2 times 1 over 25 is 1/50th. But then when I anti-differentiate the 1 over 1 plus x over 5 squared, I'd have arctangent of x over 5 times 5 to preempt the chain rule. So that's going to be 5 over 50 arctangent of x minus 5. That would be 1/10 of x minus, or 1/10 of the arctangent of x divided by 5 plus c. Okay, number 20, This one, oh, okay, yeah, I was thinking I thought it was one bigger than a perfect square because it's like, oh, 1 over x squared minus 2x plus 4. But that itself would not be a perfect square. So this one's bigger than a perfect square by 4 because the square of x minus 1 is x squared minus 2x plus 1. And I hadn't shown you one like this before, and I think that this one would be pretty unlikely. But, I think that this is good algebra, and on the homework is a good time to extend these problems. So I would say at this point, okay, well, now I'm going to factor out the 4 from the denominator. So 1/4, and then I'd have x minus 1 squared divided by 4 plus 1. Okay, and then that fraction in the denominator of my integral, I can write that as the square of something. That would be the square of x minus 1 over 2. So I'm going to say, okay, I've got all of that, and then I'm going to anti-differentiate, and that should give me something at least related to arctangent of x minus 1 divided by 2, arctangent of half x minus 1. And, okay, to prepare for that half, I'm going to divide by the half, which is multiplying by 2, so that leaves me with 2/4 arctangent of half x minus 1 plus c. That had some intrigue to it, but I think that's kind of like the upper limit of the algebraic difficulty for these type of complete the square integrals, at least in this class. Okay, number 21, 1 over the square root of 25 minus x squared. We've done ones like these a couple of times overall today and in this video, so I factor out the 25 inside the square root. That becomes a 1/5. Okay, and then that x over 5, I preempt that by multiplying by 5, and then I end with 1 arcsine of x divided by 5 plus c. And then for 22, I'm going to factor out that 4 from that things inside the square root in the denominator, because I have 16 minus 4x squared, and it's still different. And so then I've got 1 over the square root of 4, that's going to be a half. And then I'm going to kind of like refactor the square root of 4 so that I have 1 minus x squared over 4, which I can say, okay, that's x divided by 2 squared. So on the very last one, I showed all the steps. And then I've got this, and so I'm now sitting with a quarter of something that I would think is going to be arcsine of x divided by 2, but I'm going to probably have to multiply by 2, so 2/4 arcsine of x divided by 2 plus c. Okay. All right. Now that was definitely not the longest problem set that we've worked this unit, but if you worked this one on your own, it took me a while to kind of write in my answers so I could go through them quickly. But I think this was a good problem set for you for these skills. But if you still need more, let me know, because I've got a few more that I didn't put on this homework. So that's all for this one. Thanks for watching.